record. Sorry. Okay, so we're recording now. I'm just going back one slide. So this is our final, my final official lecture that will lead to an assignment. Okay. So housekeeping tips, as I've mentioned earlier. And then last week we have finished including data for AI prediction. But for your assignment, you also need to do your method section. Okay, start doing that. There's a teach one that was created by Leia, and then she did a pretty good job. So there's tips there that you can use for your method section. So today we will finally predict antidepressant response and evaluate the prediction performance of the predictions. Okay, and then we will break out into labs to do your homeworks, and then you can ask me. And okay, and then we can prepare. Then we will prepare for the next teach ones, and those that need my help as well, stay back. Also stay behind after the class, so that we can arrange a time. So that I can help you. Hi, Camila. Yeah. So I was telling them, Camila, that those who still need my help to catch up with the homework or other work, please stay back after this class so that we can arrange a time, right? Just don't leave until you get my time. Okay. So now that we have enough data to predict an antidepressant response for a cohort, we will do the prediction. We will use the reference mapping file just so that we have everything standardized. So if you don't know where that mapping file is, so you go to Blackboard, sign into our course in Blackboard. Okay, go to course content, and here is the reference mapping file. Click that. So there's two things that you need to do. First is go to File, Save As, and then download the copy. So I will download the copy, for example, in my desktop. And after you downloaded a copy, open that copy. Okay, open the copy and save it as a CSV file. Now, for some reason, reading Excel file, the read Excel does not work in all of us, even after I installed the required libraries. Okay, so and then save it as a CSV, and then we will upload that to all of us. So I'll show you how to upload later. Okay. So we'll use this for standardization. And then we will assess our prediction correctness. Okay. So we will look into true positives, true negatives, false positives, and false negatives. And we will describe those later in the slide. Okay. What are those? And finally, we will measure performance. So for our performance metrics, we will look into accuracy, precision, recall, and F1 score. So we will describe that later as well. So this is called a confusion matrix. Okay. The confusion matrix allows us to map the different combinations between predicted and actual values in a classification model. Okay. The AI that we are using is actually a classification model, meaning it allows you to classify um, data into certain outcomes. Are they positive, 1 or 0, right? So in our case, our outcome of choice is remission. So it allows you to classify or predict remission. Is it a 1 or a 0? And the confusion matrix compares the predicted values with the actual values, right? Um, so if it's predicted to be positive and it's actually a positive, then we call it true positive. If it's predicted to be a negative, but it's actually a positive, then it's a false negative. If we predicted it to be a positive, but it's actually a negative, then it's a false positive. And finally, if we predicted it to be a negative and it's actually negative, then it's a true negative. Okay. Um, a good place I saw that describes this really well in and easy to understand is towards data science. Okay, just there's a guide to confusion matrices and classification performance metrics page there, so you can just Google it. So in the same source, right, we define what are the different matrix. So when using the confusion matrix, we can now calculate how a model performs based on different factors. So one is accuracy. How accurate is the model? So it is just the number of correct predictions, meaning true positive and true negative predictions, over all of the predictions done, right? All of the predictions made. So that's accuracy. That's how accurate a model is. But its accuracy is usually biased if the data is skewed or biased. So we also balance it with other performance metrics. Okay, so there are a lot more metrics aside from these four, but we will just focus on these four. The next is the true positive rate, or precision. So it's calculated as true positive over true positive plus false positive. So that means if if the model predicted it to be a positive, what percentage of that prediction is actually a true positive? Okay, so we focus on true positives. So this is useful when you really want to make sure that it's a positive. Increasing the precision of our model is useful if you want to focus on true positives, meaning you want to make sure that that the prediction is positive, is a true positive before you act, right? Why? An example would be fraud, right? You don't want to trigger a fraud alert every time. That you want to be really sure that it's fraud before you trigger it. Otherwise, you will spend resources on fraud control that you didn't need to spend, and you will like also frustrate your customers, right? So that happens in insurance. They have fraud detection, right? And most likely, they are not only focusing on accuracy but also focusing on precision. The next metric is recall. We call it recall. People also call it sensitivity. Okay, but it's the number of true positives over actual positives. So if it's actually positive, right? If the actuals, let's go back one slide. If actually positive here, right? So the first one, precision focuses on this column. Uh, recall focuses on this row instead. If it's actually positive, how many times did the model actually predict a positive instead of predicting a false negative, right? So if you increase this metric, everything else equal, it minimizes false negatives. So it's really useful as well if you want to minimize false negatives. Like, so what are instances that you want to minimize false negatives? In clinical care, there are some scenarios where you want to minimize false negatives because, for example, you're predicting if someone will have a heart attack in the next week, right? That's your prediction, right? Then if you have a false negative, then there's someone that will actually have a heart attack next week, right? But you are not able to create an intervention because your model said that they're actually not going to have a heart attack, right? So you want to reduce false negatives. If they're actually going to have a heart attack, we need to know. That our model needs to know. So some healthcare scenarios, um, in terms of ethical considerations, right? Care providers want to care for these people, and they want to actually minimize false negatives. However, as you can see, based on mathematically, just looking at it mathematically, um, precision and recall always counteracts each other. If you increase recall, you in turn decrease precision. If you increase precision, you in turn decrease recall. So you will always have to choose between the two, right? But sometimes people do not want to focus on one of these of these measures. They create an F1 score, which is a balance between precision and recall. So it's not really precise, but it's also not really sensitive, but it's also not not precise or not sensitive. Okay, so it's just twice the product of precision and recall over the sum of precision and recall. Okay, so these are the things that we will calculate. Okay, so before we do a lab breakout. Okay, so now let me just zoom this in. Huh? Okay, so remember we had a data checkpoint from, I think it was Anne's teach one. We had a data checkpoint. So we start there. So we don't have to run everything on top unless you have an error. And then I saw people help some people that had some error, and then that's the only time that you will have to run stuff before this. But if assuming you don't have an error, let's start here. So we read our analysis df reduce pre-ai.csv that we created, right? Okay, and now we can now analyze AI predictions. So the first thing that we do is read the reference file. So again, go to file and then open and then upload your file. You know me, I always use the data folder. Okay, so I uploaded this. Okay, I will delete it so that I can show you. You just click upload here, click OK, and then search for the file the CSV file, the reference CSV file that we have just downloaded and converted into CSV. Okay, select that and then click upload. And when it's uploaded, we will be able to run this code. So we will call the data frame coef or for coefficient mapping data frame. Okay, and it will just be equal to our mapping file, the reference mapping file that we have created. Okay, we will be interested here when we see the head. We will be interested in the data column, and we will be interested in the coefficients. Okay. And for filtering this, we will also be interested in antidepressant, the antidep column, so that we can filter it to our own antidepressants and the coefficients and data columns that are relevant for our antidepressant. Okay. So the first thing that we will do is filter the data frame, the mapping data frame with our antidepressant. So for example, in this example, I'm filtering based on amitriptyline. Okay. So I'm just filtering based on antidep based on the selected antidepressants. So that reduced our data frame to only those that are relevant for me. It will be different for you. Okay. And then we will create a dictionary. So if in your basic Python, a dictionary is the quickest way to map, the quickest way to search mapping files, right? So if you have a key and then a value, it's the quickest way in terms of processing time. It's very light on processing. So just to give you an example, when I was new with Python and I didn't know that dictionaries are fast, I initially created a data frame search, right? To map it, as I searched the entire data frame of coefficient mapping data frame. That's what I did before, and then it was so slow, right? But when I used dictionaries, it became 500 times faster. So I think from 3 minutes it became 3 seconds or something like that. Okay, or something 6 minutes it became 3 seconds. But okay, and then these codes are just to test whether I have really created the dictionary correctly. Okay, so yeah, so these codes are just to check whether I did. So if I got the intercept and I check the file manually, is it really negative 4.09, right? This column dx311 is 0.15. Okay, so the dictionary will just get the data column as the key. So that's our key. We will call the data column as our key, and the value, our key is the data column, and our value will be the coefficient. Okay. And then another test for DXI, a test for DXO. You can also test for PX and RX. And then the actual test here is, are they numbers? Can I get a sum? Because right, if they're numbers, then this sum won't error out. Okay, and they are numbers. They were converted correctly. Okay. So now we have a dictionary that contains all the columns in our mapping file and their relevant coefficients. And we can create a prediction based on the logistic regression formula. So yeah, let me just understand that. Let me just open up and refresh your memory on the formula. So remember this. This is the formula that we are using for prediction. The probability of the outcome, y, meaning remission, the probability of remission being equal to 1, right, is 1 over 1 plus e to the negative this, right? The sum of coefficients. Okay, it's just the sum of coefficients. But if you transpose this, it will be it will just be p of y, which is equal to 1, is equal to e to the sum, exp will be e to raise to exp, the sum of coefficients, over 1 plus exp, sum of coefficients. Okay, so because I don't want to multiply it by negative and might forget it while debugging. When you're debugging a code, this is easier to check. That negative sign is hard to see when you're just scrolling the code. It's just a preference of mine, but you can also use this formula. But a preference of mine is that make it simple to find, to know, make it simple to know that your code is correct. Okay. So we need to import a new library math for the exp function so that we can raise to e. We can use e and raise it to a power, right? So we will create a function called predict remission. It will return 1 if the calculated probability is equal to the cutoff or higher. Otherwise, it will return 0. For this particular research, we will use the cutoff of 0.5. Meaning if the probability of remission is 0.5 or higher, then we will predict a 1, meaning we will predict a remission. If the probability that we calculated for remission is below 0.5, then we will predict a 0, meaning we will predict a no remission, right? So we will pass it our coefficient dictionary, the column names that we have for our data set, and the cutoff that we will use. Okay. We will initialize the sum of the coefficients. Okay. Then we will loop through the dictionary that we have created. If the key is the intercept, right? Because the intercept does not need to be multiplied to the value of a column, then we will just add the coefficient to our sum, okay? Or add the intercept to our sum. Otherwise, then that coefficient needs to be multiplied by the value. That coefficient needs to be multiplied by the value of that particular row, of that particular column, of this particular column. So this coefficient 0.13 needs to be multiplied by the value of this column dx underscore 272.2. So if it's 1, then we will add 0.13. If this is 0, then we will add 0. Okay? So that's just what it does. It will calculate this small thing here. This one. It will calculate that inside the parenthesis. Okay? And then your intercept is this beta 0 is your intercept. Okay? As you can see, it's not multiplied by a variable. Okay? So once we have the sum of the coefficients, okay, I'm sorry, before we also have a check if the key, if the column is in the column names. Otherwise, it might error out, right? So if the key is in the column names, then um, we add the product of the column multiplied by the coefficient. Okay. Oh yeah. So here, sorry, I created a different, I actually followed that formula, okay? So 1 over 1 plus exp negative of some coefficients, okay? So this one, sorry. This one, e to the negative sum of coefficients. And then if P of remission is greater than or equal to the cutoff, we return 1. We predict a 1, meaning we predict remission. Otherwise, we predict 0. We predict no remission. Okay. So now we can call this function using our apply method of data for data frames. So we calculate the column names. We get the column names of our data set, and we initialize a cutoff, 0.05, and then we calculate a new column called prediction, okay, by applying that predict remission uh, function on each row of our data frame, okay, and we pass it the dictionary, the column names, and the cutoff. And now we have a prediction column. Okay. So we have a prediction column. We need to check, we need to now assess the correctness of that prediction. So for true positives, a true positive is where remission is 1 and prediction is 1. A true negative is when remission is 0 and prediction is 0. Okay. A false positive is where remission is 0 and prediction is 1. So it predicted positive, but it's actually negative. Okay. And then a false negative is when remission is 1, but prediction is 0. Okay. So we have these entries, true negatives, a false negative here. At least for the first 5 rows, there's no true positives and there's no false positives because there's no prediction of 1, right? Okay, if we actually created our own model, then we can just call a function for confusion matrix, and it will display a confusion matrix for us. But we didn't do that. We use an existing model from a research paper. So we actually had to display our own confusion matrix, and this is how it looks like. So we get the sum of all the true positive columns, make it mark it as true positive, the sum of all the true negative columns as true negative, the sum of all false positive columns as false positive, and the sum of all false negative columns as false negative. And then we print it in a matrix format, right? We force it to be printed that way. So our confusion matrix is we have a true positive of 15, a false positive of 17, a false negative of 765, and a true negative of 1187. Okay, just by seeing this confusion matrix, I can definitely see that the model tends to predict a negative, right? The model tends to predict a negative. It predicts a positive very sparingly, right? And that is not within the distribution of the data, because if you see Alea's teach one, right, we actually have like roughly 39% of our data set had remission. So we're expecting like 39% of our data set should be predicted as positive, but here it's not. It's 32 out of 1,900. Okay, so that's less 2%. It predicts only 2% positive. Okay, and now we can calculate our metrics. Okay, so accuracy metric is true positive plus true negative over all of the predictions. Precision is true positive rate, which is true positive over predictive positives, so true positive and false positive. Sensitivity is equal to true positive over those that are actually positive, so true positive plus false negative. And the F1 score is 2 times precision times recall divided by precision plus recall. Okay, and then we print them out. Accuracy of this model is 60%, not that good, right? Precision is even worse at 46%. Recall is really bad at 2%, right? There's a 2% recall, and our F1 score is 4%. So this is not a very good model at predicting remission for African Americans for amitriptyline, right? And you can easily see that on the confusion matrix, right? Visually, you can see, oh, it sparingly predicts positive, but we were expecting like 40% at least are positive, right? So I will skip likelihood ratios. We will not do that. I will replace that with creating our own model next week. Okay. So this part is part as well of the teach one of Leah. Okay, I'm just reiterating it, but it needs to be done this week because it will be part of your method section that is due next week. Okay, so remember, we imported libraries. Remember that we created 2 checkpoints. We created a checkpoint for analysis DF, and we also created a checkpoint for analysis DF reduced. We can re-access those checkpoints so that we can calculate our population characteristics for the entire cohort using analysis DF, and for our own antidepressant using analysis DF reduced. Okay. So to get the number of unique persons, we just call n unique on the person ID column. Okay, and that means call it for analysis DF for the entire cohort and analysis DF reduced for our own antidepressants. So there's 6,945 unique persons in our cohort taking antidepressants, and 1,300 of them were taking amitriptyline. Okay. We also look at the number of trials with remission. For an entire cohort, we had 270,000 trials with remission. For amitriptyline, there's 780. Number of trials without remission, there's almost 4 million trials without remission in the entire cohort. Okay, and 1,200 for amitriptyline. Okay, and then we calculate percentage of the population with remission. So this is what I was telling you about. There's around 40% of our cohort that achieve remission. So that's just the sum of those that achieve remission. over the total number of rows times 100. And it's roughly the same for amitriptyline. There's 39% achieve remission. Okay. The number of dosage days, we opted to use median because if we use the mean, it might be skewed. Okay. So we use the median because a median is less susceptible to outliers or extreme values because there might be dosage days in hundreds of days. Dosage days can also be 0, right? Median will always be 60, but if there are more people taking hundreds of days of trials, then mean will be skewed to the right. And it will be skewed to the left if a lot of people are like doing a low number of trial days. And that will vary from antidepressant to antidepressant. So we chose to use median to reduce it being skewed by extreme extreme values of data, extreme data values. Okay. And it's roughly the same. The median is roughly the same from the entire cohort using all of the antidepressants and for amitriptyline. So they're both 60 days. Now, how many unique diseases were part of our analysis? So our cohort had 11,000 unique diseases, and 6,000 of them were present for amitriptyline. And finally, we also used a median for the number of antidepressants. On the entire cohort, there's a median of 3 antidepressants that they use prior to their antidepressant trials, but for amitriptyline, there's only 2. Yeah, so they take amitriptyline earlier on average, and it seems to show that they take amitriptyline earlier than other antidepressants. Okay, it seems to. Okay. So now I will stop recording.